Robin and Gary. And whoever else is missing. Who else is missing? No, I said him. Henry, turn the light out. Oh no, him. Okay, polars, here we are. Okay, so a couple of things from pre-cal. Remember that we have a polar axis. We have some kind of angle. This point, that's supposed to be a straight line, is some r theta, where the length is r and this is theta. Do you remember that? Okay, great. Remember that there are several ways we can name a point in polars. So if we want the point, let's see, 2 pi over 4. Let's just make this easy. 2 pi over 4. Okay, so here's my axis. I'm really bad at drawing these, forgive me now. Okay, see, that's not even in the middle of the circle, so that's okay. All right, so we have 2 pi over 4 would be this point right here. What's another name for that point?
5 pi, or negative 2, 5 pi, 4.
So negative 2, and then, no.
Wow.
You go negative 2, and then how much? What's?
5 pi over 4.
Negative is where when you start here, you go to the left 2. Okay, so this is how you go. I don't know why I was doing down here. You go to the left 2, and then how many is it to get around? It's, well, this is pi, and this is one more. 5 pi over 4. Sorry, you did say that. It's been like a whole year since I did this. Okay, what's another name? To which one? Okay, easy. Can't work out them all that fast. Okay, yeah. So we have we have this way to plot polar points. How many ways are there to name a polar point? Infinitely many. Okay, there were some connections between Cartesian and polar. Do you know what they are?
Oh,
There were, yes, equations. Okay, I'm going to help you. So in Cartesian, this would be the x-axis, this would be the y-axis, and you have an x component of this, and you have a y component. Okay, so what would x be equal to? Yeah, so r cosine theta. I'm going to write what you wrote, actually. So you said what? R, what did you say? Cosine theta equals r over x. So then x is, no. Y'all are killing me. So then x is equal to r cosine theta. Okay, likewise, we would have sine theta equals what? Y over r. So then y is equal to r sine theta. So those were the way that we can take Cartesian coordinates and make them into polar. This is the easy way. How do you go backwards? How do you start with polar and put them in Cartesian? That was, sorry. This was polar to Cartesian. I think I just said it the wrong way. This is the easy way. How do you go from Cartesian to polar? That's one of them, and there was another one. No. Okay, so we have x squared plus y squared equals r squared. Tangent theta equals r over x. So using these two, you theoretically can find the polar. So that's not bad. You can find the polar. Okay, so let's do convert polar to Cartesian. So we're going to do r equals, or sorry, let's just take a point. 2 pi over 3, and we're going to, this is in polar, obviously. Maybe it's not obvious. It's in polar. We want to put them in Cartesian. So we have that x equals r cosine theta, or x equals 2 times cosine pi over 3. What's that? Cosine of pi over 3 is a half. So it's just 1. Okay, and then y equals r sine theta. So y equals 2 sine pi over 3, which would be square root 3. So we could write that point in Cartesian as 1 root 3. Okay, when we go from Cartesian to polar, it's a ton of fun. Okay, so we're going to take the point 1, negative 1, and we're going to put this into polar. So we know that to find the r is equal to square root of x squared plus y squared, which is root 2. And we know that theta is equal to inverse tangent of y over x, or negative 1. What's the inverse tangent of negative 1?
At this time, please move to E3.
Negative pi over 4. Now here's the part that's kind of tricky. Do you have to pick this? Do you have to? So we solved and we got root 2 and negative pi over 4. Do you have to pick that one?
There are infinite number of polar digits.
Yes. Okay. There are infinitely many. So technically. Also know that inverse tangent has a domain. What's the domain of inverse tangent?
0 to 1. Negative 1 to 1.
It might be 0 to pi. I think it is 0 to pi. I think. But notice that the original, listen, the original relationship tangent of theta is y over x does not have, it doesn't have a limited, doesn't have a limited range. Okay, and the range is going to be the input for the inverse tangent. So you got to be kind of careful using inverse tangent. Anytime you use it, not just here. Okay.
Y over x.
300. Your calculator is going to give you an error.
You divide by 5 and you get the low y. What's the
I'd have to think about it. I don't know. You're probably not going to get one like that, but it's just good to know, to always be thinking, be cognizant of that. Okay, the graph of polar curves. So polar curves, polar graphing. Polars are really useful for what kind of graphing? Nautical. What kind of graphing is super convenient on yes, I almost said it 3 times. Gosh. Yeah, circle. Right? It's just r equals 2. R equals 2 is a circle. In Cartesian, a circle is ridiculous, right? Square root of something minus something. Yeah. terrible. Okay. Then there's also some difficult polar graphing. Do you remember these? Like limescons or petals or grace. So excited. Let me show you. This is on video. Okay, so let me show you just kind of. This would be a cardioid. Cardioids can also have little shapes like this. They have a little circle. So that's a cardioid. Anything that's kind of heart-shaped or behind-shaped is going to be a cardioid. Do it. Okay. This one is going to be a rose, a 4-leaf rose. You can also have a 3-leaf rose, which I think that you could probably understand what that is in your brain. This is really crazy polar graphing. I don't know what it is, but it's some kind of. But look at this. It's actually not a complicated formula. Look at that. It's like relatively simple, but it makes some crazy too. There are, indeed, there are. Here we have a 3-leaf rose petal inside of a 3-leaf rose petal. Sorry, I'm kind of hard to see it. Okay. I think that's. No. Okay, so graphing these by hand, you do have to learn how to do this because you are going to be asked, like, how do you find the. Curves that like circles that complete themselves, that's like makes it, it's not a function, are way easier on polar. And calculus. Now what I was trying to say. Okay, well y'all know anything about polar. Okay, let's graph one and then I'll say what I was going to say. So let's do. Okay, you need to pay attention to this because this you're not used to and it's kind of difficult when you're not used to it. So please pay attention. All right. Graphing r equals 1 plus sine theta. I graph the Cartesian first. So here we have 1 plus sine theta is going to look like this. This is going to be 2 pi. This is going to be pi. Okay. That's 1 plus sine theta, yes? Okay, now I'm going to graph this on Cartesian, and I'm really sorry. I'm going to apologize. It's coming back. Here, I'm going to put little ticks here to kind of know where we are. I have some graph paper, I think, back there that's Cartesian. Okay, so starting at 0. By the way, this center right here is called the pole. So you'll hear me say that a lot, so I don't want you to be like, I have no clue what she's talking about. This is the pole, the origin. Okay? So starting at 0 in Cartesian, okay, what are the outputs of this going to give me? So these are x values, these are y values. The output is going to tell me how far away you are from the pole. So at 0, now these are angles. This also has something to do with angles, yeah. Okay, so at 0, how far are you away from, yeah, you're at 1. Okay, now this is confusing, please listen. Please listen. Okay, when is the next time it's going to touch the pole again? When is the first time? When is the first time it's going to touch the pole? At 3 pi over 2. Okay. So stuff is going to happen, and then at 3 pi over 2, which is over here, we're going to be back at the pole. Okay. What happens in the middle? Well, from 0 to pi over 2, look, it's getting farther away from the pole until it hits its maximum away from the pole. What is its maximum away from the pole? No. What's the output? 2. Okay, so at pi over 2, it's going to be at 2. Okay, so look, we're starting here, and we're going to go, it's getting further away from the pole until it gets to 2. So you're thinking like aerially, like, I don't even know the word, but, you know, like out. What did you say? Okay, so we're thinking, what is the word for that? Is there one? I don't know, but we're thinking that way. We're thinking like spreading out from the middle, like in rays. I don't know. Okay. All right, so what happens between pi over 2 and pi? So at pi, notice that it's getting closer to the pole. Okay, so closer to the pole until you get to 3 pi over 2. So close to the pole until you get to 3 pi over 2. No, so bad. Ugh. That's not 3 pi over 2. Yeah, at pi it's at 1. That's where we should have been. I cannot believe you just said that. Okay, so from pi over 2 to pi, it's going back to 1. So back to 1. So sorry, it should be like this. And then to 3 pi over 2 is back to the pole like that. I'm really sorry. I knew. Okay, and then from there, it's going to go back to 1. It looks like a butt, but sure. Okay, here's the thing. The period of this function is 2 pi. What was the period of this function? Also 2 pi. That doesn't always happen. That's why I'm pointing that out. Okay. Yes. Okay, let's try another one. I actually like this polar graphing. I don't know why. It's kind of weird. Some people who are like pre-cal teachers usually know these, like they'll see a formula and be like, I know exactly what it's going to look like. I don't. So I think it's fun. It's like a puzzle. We're going to figure out what it looks like. Kind of exciting. You love puzzles? Okay. All right, so here we go. First we're going to draw it in Cartesian. Cosine 2 theta is the cosine curve with a smaller, period. So we have cosine looks like this. And it's going to go from 0 to pi. So this is pi over 2. This is pi over 4. This is 3 pi over 2. And I hope you can see, after we do a few of these, that not every polar graph is easy to graph. In fact, very few of them are. To what? Yeah, that's what I wrote. All right. Cosine 2 theta. So here's my graph. Okay. At 0, at angle 0, what is the output? How far am I from the pole? 1. All right. From 0 to pi over 4. Now remember that pi over 4 is like this. So from 0 to pi over 4, I'm going to be going shorter to the pole. I should have drawn this bigger. I can zoom in. Yeah, we are. All right, so from pi over 4 to pi over 2, it goes to its maximum, which is -1. So it's -1 at pi over 2. So pi over 2 is here, but -1 is going to be down here. Okay, so we have, now you have to pay attention to it's happening. So it's getting further away from the pole in the negative direction as we move angly this way. It's getting closer to the pole in the negative direction. So, closer, to -1 in the negative direction. It's going to be like this. The negatives are kind of hard. Okay, pi over 2 to 3 pi over 4, it's going to be getting close to 0. At 3 pi over 4, it actually is going to be 0, so it's going to look like this. Again, in the negative direction. So even though we're angly moving positive, it's going backwards. It's doing the opposite on the other one. Okay, so now we're at what? Pi. From 3 pi over 4 to pi. Okay, first of all, at pi, it's going to be 1. So pi is 1 is over here. it's going to be getting further away from the pole until it gets to 1. So in the positive direction. Okay. So now this is going to be 2 pi. This is going to be 3 pi over 2. This is going to be what? 5 pi over 4. Okay, so from pi to 5 pi over 4, it's going back to the back to 0. So that would be this little piece right here. From 5 pi over 4 to 3 pi over 2, which is going to be actually this little sector right here, it's going to be going to -1. So, whoops. So we have 2, -1, which would be this way. No, I lied. This way. Yeah, I feel like that's 1. Okay, and then from 7 pi over 4 to 2 pi. So this one may have been easier if we had actually gotten sectors. It's negative, but going back to the pole. So that would be this quadrant, which is actually going to flip it over here, which is going to make it go like this. Okay, we've drawn it. Yeah, then it's going to just keep repeating itself, drawing this rose. Question: what is the domain? Did we have to use all the way to 2 pi to graph it? We used 3 pi over 2 to 7 pi over 4, which is going to be in here, and that was our last little loop. Okay, because from 7 pi over 4 to 2 pi, it's going from the pole to +1. So pole to +1, that was already drawn. That was drawn here. Okay, so what is the...
No, we didn't draw that. You accidentally did that.
Okay, well then never mind. So what do you do for the next one? You draw the little loop. I don't know how I got confused. Probably because my drawing's so small. Okay, so this one, I didn't mean to say domain either. What is the period of this function? 0 to 2 pi. Was that the original period? No, it wasn't. It was 0 to pi. Okay, so this one was 0 to pi. That's what I'm telling you. Don't get confused on the domains. They're more than likely going to be different domains. I feel like you're kind of getting this. Okay, you don't wait until Sunday night. Don't wait until Sunday night to start this homework, or you're going to forget. You're going to have to look up something. It's like how to graph polars. Make sure that you're working on this starting tonight on the graphing, because the graphing is difficult. Okay, let's try another one since we have some time. Is anything that I'm saying confusing, like when I'm trying to explain to you how to do it? What do you want? Okay, so when we have our Cartesian, 1 minus cosine x is going to be down here, so no. It's going to start at 1. It's just going to be upside down. So, no, starting here, just upside down. You're always what? No. How do you draw 1 minus, why am I panicking on this? Okay, it's just going to be flipped, so you're going to start at -1. No, that's not right. Okay, it's that way, but then move down, move it up 1. Hush! So it's like that. 2 pi. Pi. Okay. All right, so we have our polar. Can y'all see all of this now that I zoomed in? Okay, from 0 to pi over 2, it's going from the pole to 1. So 0 to pi over 2, it's going to 1. From pi over 2 to pi, it's going to 2. So again, increasing, bigger, going to 2. From pi to 3 pi over 2, it is decreasing to 1. And then from 3 pi over 2 to 2 pi, it's going back to the pole. That one was so easy, that's ridiculous. I like the ones that are divided by that, by 0, pi over 2, pi, 3 pi over 2. I don't like the pi over 4 ones. Kind of don't look like that one. Okay. We have time for more. This is exciting. No, they're all pretty simple. Okay, that's taking it a little too far. Okay, 4 sine 3 theta. What does this look like in Cartesian? Sine 3 theta has period 2 pi over 3. This one is going to be difficult. This one is. It's not that bad. Yeah, okay, let's skip that one. Okay. Okay, so let's do, I should have been paying attention not to give you any homework problems. Let's do r equals, I don't want to keep doing easy ones. 3 cosine 6 theta. Okay, the period for this is going to be 2 pi over 6, whoops. 2 pi over 6 or pi over 3. Wow, this is still pi over 3. Why can't I get away from pi over 3? Okay, we're going to do one more. What do you mean? That's like y equals. Okay, 2 plus sine theta. This one's going to be easy again, but that's okay. No. Okay, so at 0 we're at 2. Then from 0 to pi over 2, it's going to be increasing to 3. Then from pi over 2 to pi, it's going to be decreasing back to 1. Not the same graph. Sorry, this looks terrible. I don't know what to, oh, because it's 2. Ugh! I do that every time. Okay, I'm going to redraw it because that makes me angry. Okay, starts at 2, goes to 3, back to 2. Okay, then from pi to 3 pi over 2, so here's pi. Pi to 3 pi over 2, it's going to be decreasing back to 1. Then from 3 pi over 2 to 2 pi, it's going to be increasing back to 2. It's a cardioid just with flat instead of an inside. Here's where we're going with this. How would you find the integral of it? I mean, we have to find the area enclosed by this. Okay, well, we're going to talk about it. It's not as simple as you might think. But you do need to know the bounds of the integral. What would the bounds of the integral be on this one? How long does it take to make the shape? Yeah, 0 to 2 pi. What about the other ones? What about this one? Well, actually, they're all 0 to 2 pi. Darn. Anyway, you have to know. Okay, what if I asked you how much area is enclosed in one petal of that? What would you integrate from and to?
Pi over
There's 4 choices. I'm looking for an integral. I'm an interval.
From 0 to 5.
No.
Pi over 2 to 3 pi over 4.
No. You were. Oh yeah, that is right. No. No. It's
Pi over 2.
pi over 4. Pi over 4 to 3 pi over 4. You have to find one of the ones that actually made it. Notice that we started here. No, it's not. No, but it's not the same. And you're going to get yourself in trouble with that mentality. Right, okay, so if we start at 0 and go to pi over 4, that doesn't enclose anything. Okay, so you got to keep going. Then we did pi over 4. Remember when then we went down here. So pi over 4 was down here. Then to pi over 2 was, or pi, let's see. Pi over 4 to pi over 2, pi over 2 to 3 pi over 4. So we got a whole leaf and pi over 4 to 3 pi over 4. Does that make sense? We also could have chosen 5 pi over 4 to 7 pi over 4. Yeah, it doesn't matter because they're all the same. So anyway, that's kind of the important part of today. Knowing how to graph is knowing how to find those bounds on an integral when we finally get there.
Petals that are horizontal